From Los Alamos National Lab. He talks about a multi-resolution approach to global ocean modeling.
So no timer. I was so looking for it. It worked so well. Okay, 9:02. So first off, I'm filling in for Jonathan Graham. Jonathan's a postdoc at Los Alamos, and he got sick and couldn't catch his flight. And he was going to talk about LES closures for mesoscale ocean models, and a combination of, and it's work we're doing together, a combination of me not really liking to give presentations on work I'm not leading, and me being very keen to present these results, a slight change of topic. We're still in the ocean, but now we're talking about the full global model instead of LES closures. And so, kind of like many of us in the room, we're interested in developing multi-resolution climate system model components, ultimately to do multi-scale global climate simulation. And so our goal for this ocean model that I'm going to talk about is supporting multiple resolutions within a single global ocean domain, conducting global and regional ocean simulations on the time scale of climate change. So we're talking, hundreds to thousands of years of simulation. And then, we're going to measure success on 1 and 2. And if we get 1 and 2 done, then it would be nice to be able to take a global ocean model and extend it into, say, non-traditional applications. Coastal modeling, estuary modeling, so forth. So our approach is to kind of pair a C-grid discretization with a conforming grid. So we heard a good bit about this scheme on Monday. We basically have convex polygons where the cell centers. This is going to be a typical low-order finite volume method. The edge separating the cell centers is orthogonal. The scheme works, and it has these nice properties. And it was put together, 4 years ago. Since it's a low-order method, we really can't run it on a mesh that looks like this. We really need to be careful about our truncation error, and so we need a very smooth mesh. And so what we use are these spherical centroidal Voronoi tessellations. The nice things about these are very intuitive to generate. We have some theorems about the mesh quality, and in particular, the mesh quality as the number of degrees of freedom increases. And there's, I think, a pretty nice review of these meshes in climate system modeling in that paper by Lee. Okay, so what do these meshes look like? I'm going to present some simulations. We're going to do a global ocean simulation. We're going to set up the system where we say the North Atlantic is what's most important to us. We want to understand what's going on in the North Atlantic, particularly in terms of mesoscale ocean eddy activity. So we're going to put a high-resolution region here. We're going to put a low-resolution region there. We're going to have a mesh transition through here. And this is actually a plot of our mesh density function. To generate this mesh, a user puts in a single scalar mesh density function. We iterate 5, 10,000 times, and we end up with a smooth mesh. A blow-up of this mesh, this is off the tip of Florida. This is a bit of the high-resolution region. You can see a couple things. One is the mesh is smooth. All of these look like fairly regular hexagons, and they're all about the same size. And you can also see, as is the custom in global ocean modeling, we fit the coastline to our grid, for better or worse. And then if we look at the mesh transition zone, what we see is it's green. It's coming from this region right there. Other than the cells being slightly larger, it doesn't really look any different than this. Mostly hexagons, probably all hexagons in this plot, regular, smooth. And so what I hope to do is to begin to answer 2 questions. The first is this finite volume approach that we've developed a viable approach for global ocean modeling? And second, if it is, can we reproduce certain regions of the global ocean system on a variable resolution mesh? So how are we going to do that? going to talk about 3 simulations. So they're going to be referred to this way. The x, they'll say by, and then the next number is the variation in resolution. So by 1 is a quasi-uniform, and then this is the region of the resolution of the high resolution region. And so we're going to have a global 15-kilometer simulation, eddy permitting. So we'll have mesoscale activity throughout the entire world ocean, as we'll see in a minute. And then there's going to be 2 by 5 simulations. So these are going to have 15 or 7.5 kilometers in the North Atlantic and about 5 times the resolution. So 75, or it's going to be about 80 kilometers in the low resolution region and 40 kilometers here. We're going to compare to observations. And we're going to answer those questions by comparing the global high-resolution simulations to observations. This is going to answer the question, is this a viable ocean modeling approach? And we're going to answer question 2 about what's the utility of a variable resolution approach by comparing the variable resolution simulation to the quasi-uniform simulation. Give you an idea of what we're looking at here in terms of computation. Horizontally, this is so 1.8 million cells in our quasi-uniform, a factor of 7 less than that in our variable resolution simulation that has 15 kilometers in the North Atlantic, and basically a factor of 2 less in total degrees of freedom for our 7.5 kilometer simulation. So this simulation, we get about 2 simulated years per day on 3,000 processors. The advantage to this simulation is it's about 1/7 the cost. And this simulation is interesting because it uses about the exact same amount of computer time as the 15-kilometer simulation, but we've done an exchange here. We've exchanged quasi-uniform 15-kilometer resolution for enhanced resolution in the North Atlantic at the price of having coarser resolution elsewhere. Just focus on, I feel compelled since I'm at PDEs to say something about the numerics. Let's just focus on the bold. So it's a split explicit, time integration, 10 minutes for our baroclinic or our slow modes, 24 seconds for our fast external barotropic mode. The only explicit mixing we have in the model is on the momentum equation in the horizontal, a biharmonic where we scale the coefficient based on the local grid spacing. And so all the simulations, we basically set this combination, and we don't tune the viscosity after that. Even the variable resolution simulations. Anytime the grid spacing is 15 kilometers, whether it's quasi-uniform or variable resolution, it's going to have this viscosity. And if the resolution changes, it's going to change by this formula to get the new viscosity. And we also have a scale-aware leaf entropy cascade. Transport monotone with a third-order polynomial reconstruction. Okay, so let's begin with a few gratuitous movies. We didn't intend to do this, and in fact, I didn't make this until after the simulations were complete and the analysis was done. But so this is the North Brazil current. Here we're in our high-resolution region. Here we're in our low-resolution region. What we're plotting here is kinetic energy, 1 snapshot per month. The North Brazil current comes around. As it begins to go up into the Caribbean, it retroflexes and forms the equatorial undercurrent in the Atlantic. And it so happened that we put the mesh transition zone right in that. And so this is a movie just to get a sanity check of what is the mesh transition doing to our simulation. This is a rather complex current. And what we happen is seasonally, as we're supposed to, we get tropical instability waves that come over, interact with the retroflecting current, and then lead to eddies that go off into the Caribbean. We have a lot more analysis that we need to do here, but to the eye, this passes the sanity check. One more gratuitous movie. This is from the global quasi-uniform simulation. So we have 15 kilometers everywhere. this is what we're targeting. This is why we're developing this ocean model, is because we're on the cusp of being able to resolve basically weather of the ocean, right? I mean, climate models have always been able to resolve baroclinic eddies in the atmosphere because of the Rossby radius of deformation of being, order 100 kilometers in the ocean. Typical climate models do not resolve mesoscale eddies. So, with the increase of computer power and some improved numerics, we think we're able to do that. And so this is what we're targeting. So we want to make sure that we do okay in terms of simulating the baroclinic eddies, and we do pretty well. Not that we can say much from this movie, other than very nice equatorial undercurrent, which I'll show more about. The Agulhas retroflexion and the Agulhas rings are well simulated, although the rings are actually much too strong. Most of them should decay here, but they continue going and hitting the current. And if we're going to say one thing about the simulation, is that the mesoscale eddy activity is too strong, and we'll see that later, not too weak.
Is that the 15-kilometer grid?
Yes, it is. And so what we're going to ask with the variable resolution simulations, we're going to have 15 kilometers, and we're going to have 7 kilometers here in the North Atlantic. And we're going to ask, do the mesoscale eddies in this region look like this? So before we move to the North Atlantic, the one bit that we were concerned about going into this was the tropical. So what this shows is, this is a cross. The next plot that I show is a cross section. It's going to show zonal flow through this cross section at 140 west. This is north, this is south, this is the surface, this is 400 meters depth. We're looking at zonal flow. Positive is out of the board, going to the east. This is observations, this is our model. This is very narrow, 2 degrees latitude, actually closer, -1 to +1. And so global ocean models always align their grid right along the equator. And to make sure that they have the flow, they maximize their chances of simulating this equatorial undercurrent, which is incredibly strong, 1 meter a second. This is about the same strength as we see in mesoscale eddies in the extratropics. So we can't do that. Our mesh is not aligned with the equator, and so there was some concern about whether we'll be able to capture the equatorial dynamics. This is observations, spot on in terms of the magnitude. You can see we're a bit too diffuse in the below the maximum of the undercurrent, but all the pieces are there: north-south equatorial currents, north equatorial countercurrents, subsurface north-south equatorial countercurrents are well simulated compared to our peers, and we even get this equatorial intermediate current, which is supposed to show up in the observations here, but doesn't. So I actually couldn't be more pleased with that result. Okay. This is OBS. So we're going to look at sea surface height. Translation for those in the atmosphere, where we're going to look at surface pressure. What we're supposed to get is a subpolar gyre. So this is cyclonic. This is anticyclonic, subpolar, anticyclone right here. The Gulf Stream is going to come up, separate, and you can see the mean path of the North Atlantic current with higher heights on your right. This is our simulation. This is from the global 15-kilometer simulation. Typically, in all of our subtropical gyres, not just in the North Atlantic but everywhere, we're about 15 or about 25 to 40 centimeters too strong. So our, our gyre is too strong by 25 to 40 centimeters. And our subpolar gyres are too strong as well, but we're actually doing pretty good in terms of the shape, particularly with the subpolar gyre. So if we compare this to our peers with the forcing, we're in the mix, right? We're definitely within what we would expect for a typical global ocean model. So then the next question is, what do the variable resolution simulations produce in the North Atlantic? So this is the simulation that uses 15 kilometers in the North Atlantic. So if this simulation was perfect, it would be identical to this. Then this simulation is using 7.5 kilometers, and then we ask the question of how do we do if we put more resolution in the North Atlantic? So this is identical to this, down to the really fine details of the structure of the separation, the structure after separation, the structure of the subpolar gyre, and how the topography influences the splitting. We see a slight improvement when we go to 7.5 kilometers. We get the axes better, and we don't get the large amplitude retroflexion as we get in the 15 kilometers. So that's the mean. This is the variance. So this is, again, to sort of map it into atmospheric sciences, this is the storm track of the Atlantic Basin, and this is looking at sea surface height variance. Amplitudes here are 50 centimeters. So that's actually, I should say, this is not really variance, this is RMS. And then we can compare it to our simulation. Well, first of all, we're on the same scale, and we shouldn't take that for granted. That's a nice result. We certainly see some biases. We see some biases in terms of the axes. We're tilted a bit. We have this donut here at the separation, which is because of the meandering, the flipping of the current north to south. And importantly, we do have the northwest corner. Eddies are supposed to come here out into the Atlantic, begin to feel the topography at the Grand Banks, and actually curve around up into the Labrador Sea. We get that. You can see it's not as wide and not as pronounced as it should be, but it is there. And the largest bias is that we get a significant amount of eddy activity downstream that isn't in the observations. So again, we'll do the same thing. We'll ask the question of how do the variable resolution simulations do? And again, this is essentially an exact reproduction of this. Again, clear down to the minute details of variance at the separation point and structure of the northwest corner. And actually the better axis is seen here, better than in the mean sea surface height. You can see the currents coming straight out, as it should in observations. The northwest corner is a bit better pronounced. We're still getting too much eddy activity downstream. I'm quite happy with these results. So this is a deep western boundary current. So this is going to show a section 26 north right through here. What's supposed to happen, very cold water up here sinks, and as it sinks, it follows the topography at depth 2 to 3 kilometers, and actually all the way to the Antarctic circumpolar current. So this is distance offshore, and so now we're looking north. So this is out of the board. Negative is out of the board toward the equator, and this is depth. Observations, the two 15-kilometer simulations, and then the 7.5-kilometer simulations. And here we do see a marked improvement by using higher resolution in North Atlantic. We're resolving the bathymetry better. We don't actually know why we're getting better simulation, but we are in terms of the deep western boundary current. It's about a factor of 2 stronger, and my hypothesis is because we're better representing the topography. I'm currently fighting with the ocean modeling upload system to get this paper into submission, but I'd be happy to share it with anyone who wants it. Where am I at on time? Ah, there we go. 18. Okay. I want to spend my last 2 minutes talking about something else, but where we're going here is we're coupling this into the CSM. We're putting it into a full climate modeling. We think primarily the biases we're seeing is due to the idealized forcing that we're using. And we'll test that hypothesis when we put it into the fully coupled model. So we'll put it into the fully coupled model and we'll drive it with atmosphere data. see if we get a better ocean. Then we will do coupled model simulations, and at some time we'll make the model available to the community. Okay, so last 2 minutes. Talk about something else. So some thoughts on global multi-resolution climate modeling. The first is that we have come, and this is not only in the context of PDEs, but in the context of this program. We have come an incredibly long way in the last 3 years. We had a planning meeting for this program in Reading, March of 2009. I'd like to dig up an agenda for that meeting, but I looked at what I presented at that meeting, and these models did not exist 3 years ago. We were talking about, what do we want to do? What's the objective? The papers that this method is built on weren't even published. They were just in draft form at the time. And in fact, I don't know if anyone presented multi-resolution climate simulations at that meeting in Reading. But I think we've had tremendous success over the last 3 years. We have a global ocean model that I presented here. We saw results from Avi presenting a global ocean model with multi-resolution. And I think we're going to hear from no less than 3 other atmosphere models that can do multi-resolution simulations today and tomorrow. So in the last 3 years, they went from not existing to existing. And what I'm doing, and I think what many of us are doing, is we're rushing through the door that this gives us significant more opportunities in how we do climate modeling. And we're rushing through the door to grab that low-hanging fruit. My guess is that within 3 years, your average climate modeler, or maybe you're slightly above average climate modeler, will be able to go and download a multi-resolution climate model, configure it with a variable resolution mesh, and spin it up on a high-performance computer. This will occur well before we have any idea of what we're doing. And maybe that's okay. Maybe we just say it's a new tool, and we put the tool in the toolbox, and we allow people that use the model to identify when the tool is useful and when it's not. But the best idea I could come up with, but I guess I'm not completely satisfied with that. We're on the verge of these tools becoming broadly available, and maybe it would be a good idea for the people, and I think there's probably 10 or 12 of us here that are developing these tools, to come together and not compare and contrast the different methods, right? We can do that here at PDEs every year and a half, but talk about what the methods in their sum enable the climate modeling community to do, and provide some guidance or just kind of lay out some framework to build from. What's the conceptual framework? What are the benefits? What are the pitfalls? What work needs to be done? And I was thinking that might be a good outcome for the program. So if you think this is a particularly good or bad idea, please let me know. And I think this is going to be the frame for the discussion on Monday. So if you're around on Monday, we can talk about it there. Okay, thank you.
Time for maybe one quick question for Todd.
I want to second your last point there, because I think maybe the slightly below average climate modeler who downloads the model and configures it, I think there's an expectation that regional climate is going to be improved by these multi-resolution techniques, and that's not 3 years away. I think that's decades away. I actually had a technical question though for you. The hyperviscosity power of 3.
Yes.
And I know we've talked about this before. In the atmosphere, they have these careful studies where they come up with 3.2.
Right.
Do you think it would be 3.2 in the ocean and 3 is this approximation, or do you think that 3.2 is?
I think it's in the. I don't think it would qualitatively change the simulations at all. We just found a factor of 10 when you double resolution. It seems to work about right. And if you take the cube root of and we got whatever we got, and that's what we used.
Yeah, Niels, I think I want to maybe push you to the coffee break because we want to move on. The next speaker is Jared Whitehead from Los Alamos National Lab. He will be talking about potential